This video is yet another step to understand the Laplace transform. As I said at the end of the last video, do stick with me through all this development. It will come together at the end. I want to eventually use Laplace transforms to deal with differential equations. So it's natural to ask, what happens to a derivative? Well, here's the calculation. Put a derivative of a function of t into the Laplace transform and see what happens. There is a derivative and a product inside the integral, so integration by parts is a really perfect fit here. Integration by parts gives these two expressions. I use a limit to evaluate the first part, and in the second part, the s can just come out of the integral. Remember, the integral is a t integral, so s is a constant as far as the integral is concerned. And once the s comes out, what is left over is just the definition of the transform of f. So the result is this. The transform of a derivative is not a derivative in the s domain. It's just multiplication by the variable s, and then the subtraction of this particular specific value, negative f of 0. This is the key idea of the whole chapter. I start with a derivative in the t domain, but in the s domain there is no derivative. There is just multiplication by s and adding some number. This makes it all work. The Laplace transform gets rid of derivatives. This justifies all of the setup and all of the work, makes all of the strangeness of the Laplace transform viable. This bizarre operation on function gets rid of derivatives, so it will eventually turn differential equations into normal non-differential equations. For now, let me move on to higher derivatives. The transform of a second derivative is calculated with two iterations of integration by parts, and the result is this expression. The main part is s squared times the transform capital F of s. That's the transform of the original lowercase f of t. But now there are two additional terms, a constant and a linear term, that get created. And there is a general form of this if you're interested. We're only going to need this up to the second derivative in the course, but here is the general pattern if you wanted, and it does hold. Higher derivatives just mean multiplying by s more times, and then adding some polynomial terms in front. Before finishing this very short but important video, let me also give you this property of Laplace transforms. In what I just did, the derivative in the t domain became multiplication by s in the s domain, plus some additional terms. And there actually is a nice parallel here. If I multiply by t to the n in the t domain, not showing all the integration work, then the result is a derivative in the s domain. This is not a perfect parallel. This version doesn't have all the extra polynomial terms, and there is this weird alternating sign, but at least it's the same sort of idea. Multiplication by a variable in one domain transforms to a derivative in the other domain, up to some other small details. And that's it for this short video, but I wanted this idea on its own just because it is such a core idea. Again, this is what lets Laplace transforms be so effective for solving differential equations. They get rid of derivatives. A derivative is going to turn into just multiplication by a variable.